Hiya, Toast, Mr. Lim here again, and here's a bit of a feedback about how you guys went on the Friyays number 2. Alright, so let's get started. Okay, so first question on it was how many moles of a diprotic acid would be required to neutralize 1 mole of sodium hydroxide. So remember that a diprotic acid is something that is got 2 hydrogens to give away, right? And if you've got 2 hydrogens to give away to the sodium hydroxide, this X is very likely to be something like an X2 minus, right? And if you're going to get X2 minus here, you're going to have Na2X, right? 2 of these protons, here we go, 2 of these protons are going to go to the OHs here, which means that you need 2 of them to react, right? And that will balance out the Na2X over here with the X2 minus, right? Making 2 waters. So the idea is that often exams will just tell you that something is diprotic or triprotic or monoprotic and not actually tell you what the acid is. Okay, so by knowing that it's diprotic, you need to know that it's giving away 2 protons, and therefore just use that ratio of, okay, it's giving away 2 protons, it's going to react with 2 sodium hydroxides or 2 potassium hydroxides or a sodium carbonate in that way. So you just have to know how to deal with just that information, all right? Many of you did, but not all of you, okay? The next one was the conjugate acid-base pair. This was done very, very poorly. Okay, so let's have a look here. Is that the idea is that it's a conjugate acid-base pair, all right? And you need to remember that conjugate acid-base pairs only differ by 1 H plus, okay? So you can only differ by 1 H plus. Now, many people went and picked this H3PO4 and PO43 minus, right? That technically isn't a conjugate acid-base pair, even though that those are on the kind of the same series, okay? The conjugate acid-base pair for H3PO4 is H2PO4 minus, or the conjugate pair for PO4 3 minus is HPO4 2 minus. Okay, so they only differ by 1 hydrogen there, so therefore the one that is the conjugate acid-base pair is NH3 and NH2 minus, right? That doesn't actually exist, but it's still a conjugate acid-base pair, or it only exists under very limited circumstances. Okay, so that's the idea, that you can't just go by, oh, what do you recognize? It's just what is the thing that differs by 1 hydrogen, right? Then lastly, the water, self-ionization of water was done pretty well, but the main one that people picked otherwise was this one here. You've just got to remember that it is actually going to need 2 waters to make the hydronium and the hydroxide. All right, this one here, you just have to memorize this table. I've highlighted those ones there to identify the types, but like once you go back, you'll be able to pick out the ones that it should have been. All right, but you've got to memorize that table at some point. Bronson-Lowry. Okay, so use the Bronson-Lowry model to explain why the pH of ammonia solution is greater than 7 at 25 degrees Celsius. Incorporate at least one appropriate equation for the answer, and you really, really should be paying attention to the fact that it's worth 3 marks. Okay, so it should be a clear breakdown. Okay, I only need 3 points. One of them is going to be the equation. One of them is going to be the equation. One should be talking about the Bronson-Lowry model, and the other one should be talking about the greater than 7 pH. All right? So if you're talking about the Bronson-Lowry model, ammonia is a proton acceptor. Okay, so you know that ammonia is a base. It's a proton acceptor, which is why it's greater than 7, but it's a proton acceptor, right? So once you've worked out that, once you've related it to Bronson-Lowry, you need to talk about the solution as a greater pH than 7. Why? Because it will take protons from water producing OH minus ions, which will make the solution basic, which is defined as OH minus is greater than H3O plus. Or alternatively, you can talk about will take protons from water produce OH minus, which will reduce the concentration of H plus. Remember, got to start talking about things in concentration. The reduction of H plus ion concentration will increase the pH above 7, right? And then finally, an appropriate equation. So your appropriate equation is your hydrolysis of ammonia, right? Many people forgot charges and states, right? So especially charges here. well, actually only charges here. Just make sure that you're putting in every single thing. It may not even say it, but you should be practicing putting it in anyway. All right. The next question, 41. So this is a bit of a typical thing that exams will do, is that they'll try and just kind of overwhelm you with information. But you've got to cut through that information and to work out, okay, what is the piece of information that is actually relevant to the question? The balanced equation for the hydrolysis of urea. Okay, so you only need for here, for hydrolysis of urea, right? Which is this in urine to ammonia and carbon dioxide. So all you really need to know is that urea turns to ammonia and carbon dioxide via a hydrolysis reaction. Now, it's not the same hydrolysis reactions that you've been doing, right? All of this hydrolysis reaction is just that it's a reaction with water. And it's a reaction with water. You just drop water in there, and then you have to balance the equation because you know it makes carbon dioxide and ammonia. Right, so the two hydrogens will go to the NH2 to make NH3s, and the oxygen will go to the carbon oxygen here and to make CO2. All right, so it's a fairly straightforward balancing equation. Just looking at saying, okay, I react water with urea to make ammonia and carbon dioxide. Right. So the next one is explain briefly why hydrolysis of urea causes an increase in pH. Okay, so this explained briefly is also reinforced by the idea that it's only worth 2 marks, but it does tell you to put a balanced equation in it, so therefore one of the marks must be the balanced equation. The idea is that why does it increase pH? Well, you've just produced ammonia, and ammonia is basic. That's it. All right, pretty much is that, especially because it says briefly, it's just saying, well, why does this cause the increased pH? Well, you just made a whole bunch of ammonia, right? And you're producing more of the ammonia because if you've done your readings, carbon dioxide is actually an acidic non-metal oxide, right? Because this is acidic and this is basic, but there's more of this, that's why it's going to be basic. And then you've got the hydrolysis equation, just like we did in the last question. All right. Next, okay, so the table, right? A couple of things. This was done fairly well, but a couple of things were done poorly overall. So you should all recognize that you need to look at the states of stuff first. And you see this water here, water being a liquid, doesn't have a concentration. So therefore, you can't really change the concentration. So none of these should have changed, right? They should have all have been 0 or like no changed, unchanged, right? Another tricky one was the idea that the catalyst, right? You've got to recognize that both rates of reaction will go up, but they'll go up equally. And so therefore, the final change to all of their concentrations will be no change whatsoever, because both the forward and reverse rate of reaction will increase, but they'll increase by the same amount, and therefore still be at the same equilibrium position, and therefore there's no net forward or net reverse rate of reaction, therefore there's no change to those concentrations, right? Temperature was done well if you could recognize that it's endo forward. Again, you have to look at the equation and see that, okay, here's my energy. It's not a delta H positive, it's a energy as a reactant, which means that it's forward endo, reverse exo, right? And then once you did that, you mostly did well. And then finally, increasing the pressure, most people got this, right? Except for this bit here. Why is the forward rate of reaction unaffected by increasing the pressure or decreasing the volume? Because the forward rate of reaction doesn't involve any gases. The forward rate of reaction is just a solid plus a liquid, and so therefore you're not actually having any gases in there, so therefore the change in pressure is not going to make a difference. All right? And then a observation, acid-base observation. Now you will need to do these ready for the test, right? So pay attention. When you read it, right, and this one's even easier, they give you an equation, right? First of all, you're looking for, in your data sheet, for colors of stuff, all right? So a green solid, that's this thing here, found on the data sheet, is added to a colorless solution, and all solutions are clear, so you don't need to say it, so it's just a colorless solution, which is your acid, your dilute nitric acid. A blue solution is formed, that's the Cu2+, and a colorless, odorless gas is formed, that's the carbon dioxide, right? You can't just say it's a colorless gas. You can't just say it's an odorless gas. You have to say both of them. So both are needed, right? Couple of things, don't name the chemicals. Once you've named the chemicals, you're not writing an observation, you're writing an inference. Okay, and then when you're looking for reading this thing, right, you actually need to really read carefully whether it's in what's in excess, okay, or if a small or a large amount of something is added to identify that one is a limiting reagent, which will change the observations, right? If your copper carbonate is in excess, then your blue solution will have a green solid in it because the copper carbonate isn't soluble in water, and if it's not going to get dissolved, there's just going to be a little bit left over at the end. All right, so blue solution with green solid inside it. However, if the nitric acid is in excess, then a blue solution is formed and all of the green solid dissolves. Right, all of the green solid dissolves. This question isn't written very well. It's missing that information. You really shouldn't get a question which has no information about which one is in excess. All right, so you should really be looking for that. And if you do not find that there's information about anything in excess, you can, if it's in class, you can ask. Otherwise, you can assume they're at stoichiometric ratios, and therefore it will react to completion, and both of them will be fully consumed. Right, but that's going to be rare. We really should give you information about it being in excess or not. Right, so that's it, and I will hand back your results later on. Adios.